So this is going to be kind of an experimental process of we go through a design. I need for an experiment for a project coming up a really smooth pulley for a cable that has a lot of memory in it and twists very easily. So when we used this last time, we went to Lowe's, Home Depot, pick your favorite hardware store, and we bought a nice 2-inch pulley with a standard pin in it and the little cast body. And every time we kind of did our clothesline, it hung, and then it jumped, and then it hung, and then it jumped, and then it did some more stop and go, really jerky movements. All right, so it was not the kind of thing that was ultimately desirable. It got us through the first stage of our design process, but it did not exceed. It barely met the requirements. It did not exceed the requirements. All right, so one of the things when I look at GD&T is we're talking about application that at the end of the day, to make this make sense, you really need a project. You need parts that fit together, because we said last week, a block that sits on the table and doesn't do anything really doesn't need any GD&T. It hardly even needs any dimensions or tolerancing at all. And go take find a chunk of material and cut it off on the bandsaw and set it there, and it's a work of art. Right? But what we end up coming down to is, at what point are we going to put things together, and does it even need GD&T? Can we get away with straight tolerances? So I'm going to do what's called a top-down assembly. This is not something that we go that far into. It's more of a honorable mention even in the Solidworks class, because it creates external references. It has tricks and traps to it. So I'm not expecting you to be able to produce this model. I'm going to upload this to Canvas, and you'll be able to download it. So when we go to the drawing phase, what you'll be expected to do is bring those parts in and apply the dimensions and start to make those connections of why this piece had flatness, why this piece had a positional call out, why this, where those combinations came in and why they were critical to this design. Right, so as we go through the process, so right now it automatically asked me to bring in a part, which I didn't really want to do, so I'm going to go ahead and cancel out of that. And I don't mind that it starts the command, but I really don't want it to do an automatic browse. That's kind of annoying. And I don't mind the preview. Making virtual, in a sense, that's what the parallel experiment last week was doing, was to have virtual components inside of an assembly that were being driven, that had those buildups to other pieces. So I don't want to overload you with SolidWorks terminology, but give you enough of a background that you can kind of see where these terms come from. And then an envelope is a way of managing how big, kind of where the parts all fit into. And then the rotate context toolbar, once we pick a part, the little box will come up and allow us to manipulate and maneuver. All right, I don't want to do any of that, so I'm just going to go ahead and close the begin assembly. All right, so where I made my first mistake last week was we pulled the parts in, and I made an assembly, and when I went to make those in-context parts, that top-down virtual components for the parallels, I had not saved my assembly. So file structure and documentation, we need to decide on that early on. All right, so as we go through and list our specifications, the things to pay attention to are the nouns and the verbs that we're using, because the verbs will tell you where the scope of work really becomes critical, and in a sense, where we're going to apply the GD&T. All right, so I need a folder, and I don't, oh, no, I didn't want to do a save. And we're in documents, and so I need a new folder, and this is going to be my example. And for the assembly, this is my really ultra smooth. Oh, lost something there. Wasn't paying attention. Double click. There we go. Ultra smooth pulley, and that creates a file. And because of the external references, once I create this name, I really just want to be happy with this name forever. I don't want to have to change it if I can all but help it. Okay. So one of the things that we do as far as development, and we'll get into it in the Solidworks class later on, or as in previous videos, is a layout sketch. Well, within an assembly, the layout sketch is going to start to tie things together. All right, so rather than having to remember dimensions and build those dimensions into each individual part, I can streamline my process, but I'm taking a risk. And that risk is if I break one of those relations, or the software loses its mind, or I lose a part, there is a potential that I will end up with all those fun little yellow and red explanation points. You have issues. All right, so I need to pick my orientation, and we'll go to the front plane, and I'm opening up the sketch. And so pulley has a wheel, and so I need to decide how big and where it's located. So the hub, I actually need to find a bearing, and that bearing will determine what this diameter is, because we will have a fit. I need it to be a press fit. I don't want it to be such a hard fit that I collapse the bearing and it doesn't really do what it's supposed to do. And then on the pulley side, I want this to be pretty good size. I want it to be larger than the 2-inch pulley wheel that we had, but I don't want it to be humongous that it becomes something difficult. So pretty close. I'm okay with the 4-inch, just rounding. And the thing to keep in mind going into the design process is this is an evolving process. I'm making hundreds, if not thousands, of little decisions every step through this process. All right, and then this is the point, kind of our jumping off point, that as soon as I step into this, I look past those specifications of I want a nice, smooth, rolling surface. I want to be able to hold an 1/8-inch wire that has some twist to it. I want to be able to mount this thing in kind of a clothesline configuration to where I can feed it out and feed it in as smoothly as possible. All right, so there's those verbs that are telling me these are going to be a little more critical when I translate that into the geometry. Okay, so one of the things we can do, and I like McMaster. So we pull up McMaster.com, and I type in bearing, and we have bearings and bushings, and would like to just have a standard ball and roller bearing, and I think I double clicked there when I shouldn't have. All right, and then we start again kind of going through how much do I need, what do I want to spend. This is not a high speed, there is a little bit of load, but I think I can probably get away with a standard ball bearing. I don't know that I would want to go to a light duty, use these bearings where high speed and precision are not required. Well, I do want a little bit of precision, so maybe not on that mix. I haven't seen the hex bore. Those are kind of cool. Electrically insulated. That would be kind of nice if we were going to drive this or had any kind of static coming off of our system. So let's just go into the standard, and then we'll pick a style. So the open style is, all right, so when we talk about lubrication, permanently lubricated and shielded, and then actually going to sealed. So you kind of look down through the descriptions, dissipate heat, block out dust and contaminants. That's kind of important, especially if there's any kind of plastics that are going to rub, and as they rub, they're going to pick up the dust or create their own dust. And then the seal bearings block out dust and but retain the most heat. All right, so probably we'll just go with, I'm kind of thinking that this is going to be sandwiched, so the open or the shielded would be all right. I don't want to spend too much on them. So then we get into the numbers. All right, so the shaft diameter, and this is where I start thinking about fasteners. All right, with fasteners come fit. And as we start to drive those, that is also going to be one of our tolerance stack-ups. All right, so if I were to go with a 3/8 inch shaft, I'm pretty sure that I can get a shoulder bolt that will act as my axle that this will sit on. And housing ID of 7/8, and it is 7/32, which is about 219. All right, so just under 220 thousandths. Way over for dynamic and static. I'm not going to be anywhere close to 750 or 310 pounds, but I also don't want to put the my little shoulder bolt into too much shear and find out that I'm going to over design it. All right, I also want something that's easy to work with and machine. So at 7/8, I think I can deal with that one. So when you're dealing with a company product, we can come over and we'll see that, yeah, I think $6 is in my price range. The ID tolerance of -0.3 of a thousandths to 0. Okay, then I can fit that. And the width tolerance isn't so much of a concern. And at 220 thousandths in width, yeah, I think that would work out on my design side. And I want to save this to a 3D Solidworks. So it saves. It ends up going over into the downloads folder. Well, let me see, I'm kind of bouncing around here. There we go. So we go into the downloads. I'm going to pick that ball bearing up, and we'll put it over into the documents. All right, so I don't need that right now, but since that's my selection, that's what I'm going to go with. All right, so on the design side, I have a theoretically perfect. These pixels are out to millionths, if not billionths of tolerance. All right, the calculation, the mathematical calculation is that these drawings, these models are theoretically perfect. So the decision we have to make is, do I start out tolerancing them? Probably not. I want to go line to line because that's going to be my fastest way to develop the concept. If I make changes and go through the rest of the process and it all falls out that at the end of the day, that's what I end up with, then great. If I start making changes when I have a 90-95% complete model, that my design is, I am fully committed. We've been through the design review. Everybody's happy with it, or at least I'm happy with it. Then we can go ahead and start thinking about tolerances. All right, so the 0.875. The one thing that I did not catch is that under the units, and let me fly this in, I do want to work in 3 or 4 decimal places though. And again, depending on the precision, it may be to our advantage. We are in inches. It may be in our advantage to go to 4 decimal places, but at the very least I want 3. All right, so when I type in the 0.875, I'm seeing 875, I'm seeing 4.000. All right, so that is the body of my pulley. So my first 2 decisions were really just setting up this this diameter and coming to that conclusion. All right, so if the bearing face or the bearing OD is +0 -0.4 of a thousandth, then I probably want to make this hole about 874. So there's about a thousandth press fit. All right, I wouldn't want to go. I wouldn't want to go bigger. So I got to kind of start thinking that process of how much material am I going to have? What is the most material that I can build into this and still have a working element when I get done. All right, so this needs a housing. I want to tie this together. So I'm just going to use a center point rectangle and say it looks something like that. All right, so one of the things with the design, and especially on the concept side, is this going to be a little messy. There's going to be some chaos, and it's by far not going to be perfect going through the first round. All right, so if I were to make this, let's go 4 1/4 inches. So just 1/8 of an inch over size. And I'm not sure that I want these to be equal. So going back to the relations out of SolidWorks, 4 1/4 by 4 1/4, this may end up being 4 1/4 by 5. It may end up being 4 inches by 6. I don't know yet. All right, so in this case, I'm not going to start driving relations that that may end up being in conflict later. If I can look into that magic crystal ball of design intents, dealing with all of our tolerances and all of our stack ups and everything else, and also be able to see where these relations are going to end up, then I'm going to build in some of that intelligence early and often. So if this is my mounting plate, and let's see, what is another critical piece of information? I need a 3/8 inch hole, and I'm not sure if my load calculation is going to require a bushing to be pressed in so that it can carry. And my materials, we haven't really talked about materials. I'm thinking aluminum. This doesn't have to be, it has to have some wear resistance, but the amount of use it's going to get over its lifespan, I don't know that it's worthwhile going up to a steel on the pulley side. And aluminum being relatively easy to machine and manufacture, I'm thinking that worst case, even if I wear this one out, I can make 10 or 20 more just once I have the programs, once I have the product developed, and then decide, we've run through a bunch of pulleys, it's time to make one out of steel or stainless steel. So that being the case, I said I was going to have a 3/8 shoulder bolt. We need to look at that stack up of how those are going to work. But a 3/8 shoulder bolt is going to be about the same. It's going to have a plus nothing dimension, or typically a plus nothing dimension. So let's take a look at our shoulder bolts. Okay, shoulder screws, and we'll just go, well, probably will want a precision. So I'll spend a little bit more money, and to go slotted or to hex. Natural tendency on any is just to go hex, or go with the hex key for the tightening. So shoulder length, I don't know yet. The thread length, 1/8 of an inch. That's we're in the really small ones. I need to scroll down a little bit. All right, that looks a little bit better. So plus nothing minus 1/1000th. So that bearing inside diameter, I didn't grab that one on my list, but we're going to look at this being a minus dimension. So minus 0.001 to 0 on the diameter. I should have took a screen snapshot. Maybe we'll back up and do that. And so I need, I'm not so concerned about the thread length. We may end up having to go down a little bit. Or I just decided if I'm going to let it stick out the other side and put an acorn nut on it. Let's see, what else can I do here? Shoulder diameter, and then the shoulder length is probably going to be quick stack up, 1/4 inch, and 220 is going to be real close to 3/4 of an inch. And then the thread, and actually we need to be a little bit undersized, so a 5/8 with a 1/4 All right, so best guess. I just want to see what those tolerances are, and we can take a snapshot. So if I come over to Windows and I go to, let's see, am I going to be able to find that? Nope. Then we're just going to go to the search and type in snip. And we'll grab the snipping tool. And I really just want to, oh, it popped up over here. And don't really need to have all that much. Probably should have got a little better description. And when I save this, I'll save it back to my my project. So as we're accumulating this data, the purchase components have just as much effect on my tolerances and my decisions as I am as the parts that I'm going to create and manufacture. All right, so if I back out of that, maybe back up a couple, get back to the, okay, so same thing, ID at 375, ID tolerance minus 0.003, oh, and the OD tolerance minus 0.004, so we will create a new, and maybe this time I'll throw the ball bearing description in there. All right, so some form or fashion, whether I print this to a PDF, I need to create that documentation trail so I can reference back to it. And I think that was an R6, so okay, so we can get that out of the way. And then we'll fly that one. Okay, so each of those components, each of those pieces comes becomes part of the effect. All right, so I need to be able to clamp this together, have it act as a shell. We have lots of choices. Each of those choices comes with an associated part. So if I were to wrap this, I'm going to have a lot of stability if I put a 1/4 inch or a 3/8 inch plate around this, and I would have to grow my my mounting plates by an associated amount to leave room for those points. So the other option would be to put a standoff, and the standoffs I could hold pretty decent tolerances, just having a small ring. And then also it would satisfy the, let's see if we can jump in here, and I'll try not to, let's see, those are going to be, let's see, threaded connecting links. Okay, so if I have a carabiner or a threaded connecting link, I need to hang this, attach it so that it goes to a post or whatever. And so if I just were to loop that, I'm concerned about the opening width. I would like to have it for stability meet most of that size and not jump around. But there again, I'm looking at what is critical to my design. So if I went with an opening width, 9/32 is pretty small. Probably would want to go, let's see, the thickness, well, 1,000-pound capacity, so load really isn't an issue. What do we have? Maybe a 3/8, and then the 9/32, and what do we have for an inside width of 11/16? All right, so if I were to put a 3/8 in there, 375 from 875, that's about a 1/2 inch, so a 1/4 inch on either side for it to move around. All right, just that quick math tells me, am I going to be satisfied with a 3/8? The other thing is that 3/8 on the opening, am I going to be able to force an actual 3/8 in there, or is something else, is that not going to be big enough? All right, we've got to start somewhere. So I'm going to come up here to the corner and I'm going to put my first post. And to go through, so after we overkilled this with a 3/8 shoulder screw, which gave me a decent sized bearing, then now I'm looking at going to now a 1032 for clearance. So I'm going to put in another piece, and 375 on the diameter. I may have to shrink that a little bit once I just determine if that threaded link is going to be able to tie in. So on the Solidworks page, I think I will have to put it on this page as well because it's one of those handy things to have. We have a formula. So a 1032. If we're working in metric, well, that's kind of a different set of clearances, but we're still in the same numbers. So a number 10 times 13 plus 60 should give you 190. We divide that by 1,000, that will give you a major diameter of 190. And then depending on how much I want to allow this piece to move, right? So if it's at 190, but manufacturing processes, it's going to be about 187, 188, so right there at 3/16. I don't want to have to pound it in, but I don't want it floating around so much that that it becomes, kind of the, becomes kind of a headache as far as assembly or otherwise. So maybe we'll go with the 190. And again, that's something that I would want a tolerance later on. All right, so coming off of the side, well, that loop is going to kind of come around this way. There's a little bit of gap. The thickness at, let's see, that thickness at 9/32 was that it? Probably need another picture. Let's see. Yeah, so this is where being able to manage your fractions comes in handy. 9/32 is 281. The bearing that I picked was 7/32, and that would be 219. So there's a little bit of an issue all of a sudden with the thickness of this piece unless I want to do more design and create clearance in these plates to make that work. All right. Decision on top of decision on top of decision. And we have all of these decisions to make before we ever get to the really serious tolerancing. All right, so I'm going to kind of speed up a little bit here. We'll give it at least 1/4 of an inch. That puts it in place. We'll go with a couple of center lines, and I'm looking for the origin over to the midpoints. And at least for right now, I think that I want this to mirror. And then I'll take those 4. And after I have the 4 corners, then that gives me a location for those pieces. So I think we've spent enough time with the design portion of it, considering those tolerances, building up into those tolerances, but it's time to make some parts. And let's go ahead and make sure that it gets saved. Oh, that was interesting. I didn't think I told it to. But that did the end result. And so my sketch 1 that has all of this geometry in it is now going to be a layout sketch. All right, so again, I'm going to provide you with these parts so that you can put them into the drawings to apply the tolerances, the dimensions, and go through that sequence. All right, so looking at this, one small problem, all right, one very big problem is that if my cable comes over and wraps around the pulley this way, I've now run into 2 of my standoffs. So that hole, I'm going to have to make adjustments to my height, to my geometry. This is where it plays out. So if I go up to 4.5 and then rebuild, well, I'm still not quite tangent. So I'm going to go back into that sketch and we'll use the center line. And I just want to see, I'm envisioning the wire coming in from the right there. So bring it off to the side. And so, well, I don't know why I did that. So apparently my left button is a little touchy. All right, so at 5 inches in height, all of a sudden the cable is just barely clearing, and I don't want it to rub on the bottom side of that. So maybe we're up to 5 1/4. All right, so that, I don't think that's going to affect the balance. but I now have enough clearance. Oh, I guess I should make sure, since that didn't get a horizontal relation, now I have enough clearance that even as this moves around, it may rub on the standoff, but it's not going to affect the clearance. So the other thing would be that at 375, if I was to bring this up closer to the corner, I really don't need this extra material. So as I play these what-if games, then if I bring that down to point, well, do I want to go to the fractional? Yeah, let's go 3/16 on the fractional. So 1875. And now I have quite a bit of clearance. I can bring that down to 5 inches. I'm still at a nominal size. And at the very worst case, is it going to hurt anything if and because it's not a square anymore, my assumption of the relation now has a small problem with the gap up here. All right, so do I want to make this 5 by 5 so that I can keep the 45 degree? Probably not. I think it's going to be easier that understanding the problem with the relation, then I can break that coincidence. Come back, 1875, and now I have tangency to both corners of the part. All right, and I can check it against each of the corners, and now I have a lot more clearance. So can I get to 4.75? I'm trying to minimize my material usage. No, right back to where I started. 4.875. Okay, maybe. But I'm having the gut feeling that 5 inches was a good number. All right. So in the design process, we're going through what are our nominal numbers, what kind of dimensions can we get away with, and then once we have those dimensions, now we're kind of into that point where we can start building. All right, so we go back through what we did the first night of safety. And do I have pinch points? Am I going to hurt somebody with this? Okay, am I going to hurt myself because I'm probably going to be the one operating this? As I move this back and forth and I'm running the cable in and it catches, I have this opening. I haven't even created a 3D, any of my 3D parts yet. But those are the things that I'm starting to think about, is how can I minimize, align, otherwise make this thing safer. Well, part of the problem is going to be until we actually have something that's operational. I'm not quite sure where that one's going to fall out. All right, so let's go with. Okay, well, we have the layout. All right, so in SolidWorks there is an actual layout, and because I have run into problems with the layout and it hasn't really been satisfactorily, now I haven't checked it in 2019, so I will have to create my 3D sketch and see if my 3D sketch operates under the same in the same ways that I'm used to it, and the layout sketch creates problems, or if the create layout versus the lowercase layout is still the better option. Either way, I have this sketch that's now going to drive 3 or 4 parts. All right. So to make that happen, we're in the assembly, and under insert components, I'm going to create a new part. And I don't really want to tie it to a plane. And looking at the terminology now, this part is going to be fixed. You do not want to float this part, period. End of conversation. Very bad to float the part in this situation. Any virtual components, any externally referenced components, they need to stay there. They are being built in reference to this sketch, and anything that you do to move them or try to move them needs to be driven out of this sketch, not the part individually. We can make modifications, but this is that risk element that we're talking about. All right, and then the other thing is with the brackets, these are now virtual components. So our first pass through, these are all going to exist in the assembly. When I take this out into the drawing, I really need to have these 4 separate components. I can't really have, I can do the virtual components, but it makes it more difficult, not less. All right, so if I expand that out, there's just like the normal part that we created our 1, 2, 3 block. We created some of our pieces with, and I need to right click and edit the part. And on the front plane, which now lines up with the assembly, I open up a new sketch, and I think I want to do that that pulley first. So the choice is, I automatically went in to draw the circle, but the choice is that I can convert those entities. So by selecting on the sketch item and then converting that entity, it's now tied directly to this layout sketch. All right, so in my experience, I have a very high hesitation to tie virtual components and top-down assemblies part to part. It does not bother me to tie it to a layout sketch because it's a single point of failure. Right? If I have part 1 and I tie parts 2, 3, and 4 to the part before it, so part 2 is tied to part 1, and part 3 is tied to part 2, and part 4 is tied to part 3, and maybe part 5 is tied to part 1 again, and all of a sudden I delete part 2. Oh, I don't need that one. I've pulled that one strand of the spider web that is going to cause the whole thing to collapse. All right, if I have a single point of failure like this sketch, I pretty much have one place to look. I have one place to create those problems and to deal with that point of failure. All right, so again, this is kind of on the design side. This is the advanced portion of it. I want to give you the how I got there and the process of making those decisions before we start putting numbers on it, and kind of, it really does look from the outside haphazard, and to a certain extent some of it is. We're taking our best guesses and then everything that we know building into those into these geometries. All right, so my next one, I could have created a sketch that would also set the depths. All right, so a lot of times I would create a 3D sketch, but I figure I'm gonna have everybody looking at me like I'm out of my mind anyway, so putting the 3D sketch into the mix, not yet. We'll play with that one a little later. All right, but this is just like we're in a part, and if I had any other components, they would be in transparency, and the blue is telling me that I'm in that top-down assembly. I'm editing that part. So we're going to extrude, and I think my 0.22. Now bearings usually have a little bit of relief, so the 0.215. So on the manufacturing side, if I'm doing my due diligence and saying I'm probably going to start off with a piece of 1/4 inch, I'm not really going to grab a piece of 3/16 because it's already close to a 32nd undersize. 15 thousandths aside I could probably live with, but if that bearing really took a load, I would want the interface to have a bigger contact patch. So I really want it close to the 218 to the 220 that we talked about. So my first guess, 0.21, well, 21875. And I only know that because I've done it a million times. Okay, 10,000 times. 7 divided by 32 for my 7/30 seconds. 0.21875, which comes back to what we set for the thickness out of the catalog for, now I can't see it, it's right in front of me, the width of 7/30 seconds. And a plus or minus 5, that becomes part of the deal. So going to 1/8, maybe I want to take that down to 210. All right, 4 thousandths aside I can deal with. 15, 16 thousandths aside, I'm not so sure about. All right. So the other thing would be I wait until the bearing's been delivered and I measure it and say, oh, I want it to be the exact same size, but we really don't have that luxury. All right, so I'm going to make it a midplane. I'm going to build this all on the midplanes so that we can drive those dimensions. And so that creates a pulley. And then I want a V groove. So I'm not going to set this. I'm probably not going to set this up in a lathe. I'm going to take a 4-inch chunk of material and try to cut to the center. I'm going to clamp this down in the mill onto a tooling plate, so that whole stack up of subplate to vise to parallels to material, or basically just go from the table of the machine to the subplate, and then I have my clamping. All I have to do is make sure I have the flatness between the table and the subplate, and then that my clamping surface is also flat and perpendicular to the spindle, to the head of the machine, to the tool. All right, so that being the case, I don't have a problem starting off with this material, clamping into 4 corners and machining this flat, and then cutting around the outside, flipping it over and maybe taking a skin pass. Or for that matter, 4x4, I think I could probably hold on to a 1/4-inch piece, take a skin pass, ensure that I have that flatness on the first machining operation, and then flip it over onto its flat to flat, clamp it down, machine this side to be parallel, and then make the outside and the inside cuts. All right, so that's a lot of machining jargon that if on the design side you don't take into at least some account. Back to one of our first rules was the drawing does not dictate machine process. Right? We're going to suggest, we're going to think through whatever our experience. I'm certainly not going to make this with a hacksaw and a file. Right? And so going up to, even if I put this, I drill the through hole and I clamp through and I turn this on a rotary on a manual machine, I'm still going to have to pick equipment that's capable of holding the tolerances that we're determining in our process. All right, so let's see, that is on the midplane, so I'm building out symmetrically. And so the bearing, so I need to get out of this. Oh, no, I don't. One more. So I'm going to go ahead and complete my design on the top plane. And I want to temporarily hide, so if I right click, I can click on the little eyeball, or we can do the little flyout, and the first item will hide that sketch. So I kind of want it, I wouldn't mind it being tied to that sketch, but for the most part, I'm just going to create my V group. So at 220, that's a little bit deeper than I wanted to go. And so I have this habit from creating swept threads, and I will stay with the habit of using a thread mill that I can come in with a 60-degree sharp V and just make a pass. And even if I had to do this in 2 steps, clamp half of it, run 180 degrees, clamp the other half of it, run 180 degrees, I'm reasonably confident in the machine and the tool to be able to line those up and not be a crazy tolerance. The other thing was, we said we had an 1/8-inch cable. I do not have a construction circle, so it's going to be about 125. Oh, and my parts staying on that, so I'm going to add, did that get a midpoint? Oh, that did get the midpoint. All right. So then we want to, I don't want it to be like right on where it can roll up and over out of the edges, but I don't want it to be completely subflush either. So I need a tangency, considering how that moved. And I know that the tool that I'm thinking about is 60 degrees. So that really doesn't look too bad, except the height is a little on the annoying side. So maybe I would have to measure that tool, but if I could get it engaged at 190, there's just a little bit sticking up. And I have the angle, so what else is able to move? So that didn't quite get to, oh, went to the midpoint of the other one. All right, so coming across that face, nope. I'll make sure that I'm completely looking at it. There is supposed to be a silhouette edge, but I'm not quite getting that, so that's annoying. So I'm going to go to my next in the bag of tricks and make the center line coincident with the origin, since I went to midplane. And now I'm kind of stuck with that midplane. I really wouldn't want to change it because it's going to change how this V interacts with the other part. All right, and then the next one is that we don't have a construction circle, so I'm going to switch that to the circle. And then I need one more center line to act as my axis of revolution. All right, so on the features, I want to revolve cut. We're removing material. And then because there's more than one center line, I'm going to pick that point and make that my V groove. All right, so all of that to get to the pulley. And then I'm going to rename, so this is the pulley and the pulley assembly. All right, so we'll see if we can get the design going. All right, so the check then is that I need to insert a component. I'm still going to use my my layout sketch, and the MasterCard models have this habit of the revolve sketches, the sketches in general coming in with their geometry. Okay, we get that cleaned up. I'm going to make concentric, and I know I'm going through this kind of fast because, well, I'm not really expecting that you will, well, that is on the midplane, that you will want to create all of this geometry. All right, so the front plane to the midplane of the bearing will go coincident. I look at it from the front, that looks pretty good. Look at it from the side, I have a little bit of protrusion. All right, so that's my clearance, so that I'm not rubbing to the side plates. And then as far as being able to turn, all right, so with that concentric mate, there is a lock rotation, and that will get me to the point to where the minus sign goes away. It doesn't move unexpectedly. And I know that this is going to turn, so I really don't need to see it turn. It's a circle, or it's a, it's a cylinder. There's not really much there to worry about. All right, one more. All right, so let's go with the plate. And so another new part, and no, I don't want to tie it to anything. And then this is going to be, if I go with a mount plate, so naming versus numbers. At some point your company and your design team should have already resolved this. So, so a lot of times, at least for now, since it's still in a virtual state, I will do plate 1 and plate 2, or plate left and plate right, front and back, something that makes sense but isn't really that critical. And so I'm editing the part. We're going to pick up the exact same thing. So the advantage of the 3D sketch, or having another sketch to set the depths, is that I could drive all of these depths from that sketch. All right, but that again is another level that I had to screw up a lot of parts before I kind of developed that technique. All right, so let's go ahead and select the chain. I'm in the sketch. I'm going to convert the entities again. No, I'm not in the sketch. Let's go to the front plane inside of the part and open up a sketch. Now I can select the chain, convert the entities. All right, so you can kind of get a sense that this is a very fast process. Once I put the development into my layout sketch, then I have all of these things to work from. All right, so on this one, we're going to have the clearance. And actually, since it is the clearance, I'm just going to go ahead and we'll convert those entities as well. and then the through hole for the shoulder screw. Right? And then we go back into the features, do the extrude, and now this is starting on that front plane. I want to shift it. I'm going to offset it. Let's see, we're at, what do we say, 730 seconds? Well, that makes it nice and complicated. How about 0.21875 divided by 2? So 109.3. Ugh. All right, so can I live with a 110 there? A little less than a thousandth. And the bearing has the potential to be up to 5 thousandths small. And my deck is already at 110. So, you know, again, I'm shifting one way, and now I'm shifting the plate another way. And it also helps a little bit with math that the standoffs will be tied in to you know, basically end up at 220. Right, and then I don't really want to do a lot with this plate, so if I make it 250, then we're shifting the sketch. Let's go to the top view, and maybe we'll see it. So we've shifted it over to have just that little bit of clearance to the bearing, and then whatever thickness I've created for that plate. So the flatness tolerances, the runout tolerances that we're going to start considering is, if this wobbles, it's going to rub. And then if it rubs, it's not going to be smooth, which was our initial design criteria. Okay, so I'll go ahead and accept that one. And I look at the plate. It's pretty straightforward, has the geometry in it. And then I can go to the next plate. So we'll accept that one. And on the keyboard, I'm just going to hit Tab, and that will hide the components. I'll just go down the list. It was getting kind of busy. And one more rebuild, one more save. And it's going to warn me that my virtual components need to be saved. And I need one more, so let's see, insert component, new part. And the difference here is that on this side we created clearance holes, on the other side I need threaded holes. So don't want it to tie to anything. And so this is going to be plate 2. And if I think about naming first, then I will usually name first. If not, then we pick it up. I have started a sketch within the context of this assembly. Oh, so that's a nice little warning that they came up with, is I'm not actually editing the part. And the sketch that I created is down here, so everything that I build will be at the same level as this. So that's not really what I want. We'll discard changes and get back into the part. All right, so same things. Select the chain. I can control select the through hole, and I want to. Oh, I still didn't get a sketch. Darn it! All right, so the front. Now I have my part. Just did a quick check. Convert those entities. And then same thing, except now when I go to do the extrude, we're going to offset it. We set 110 thousandths. And I want to offset it the other way. And then I want to reverse the direction. So on the design side, it's a little bit weird to pick that sketch up, move it over 110, and then continue in that direction another 1/4 inch, but it gets us to the desired result. All right, so what I didn't do was the threaded holes. I want to do that with the hole wizard. So I'm picking that face, and we pick up the hole wizard. This is going to be threaded. And let's see, I took a snapshot. What did I do with it? And do I have my previews turned on? Maybe not. All right, so large icon. Oh, there it is. All right, so thread size was 1/4 20. Want to make sure to get that in. So actually, Oh, that was for the through hole, so I can pick whatever I want. I picked a 1032, so as long as it has that compression from one side to the next. All right, so I got myself a little confused there. ANSI inch, all drill sizes. No, that tells me that I'm creating clearance hole, which I already have. I want threaded, and we're going to do a tapped hole and go to a 1032. And it can stay through all. I don't need countersink. We'll leave the call out. Class 2B fit is pretty much standard. We can include that, and that's going to be pretty much another whole discussion of Class 1, Class 2, Class 3, and then the H classes in metric. All right, so positions. Advantage to the layout sketch is I'm just going to pick those 4 points. And accept. And now, because these parts are symmetrical, when I go into the drawing and I start tolerancing, I'm not as concerned about, if this side is flat, that this side has to be parallel. For the most part, I don't care about this side. All right, as long as it engages and I have the clearance, those are my critical dimensions. The outside, as long as it as everything clears, I'm considering it good. All right, so the one thing with the assembly then is that let's go ahead and hide that one as well. I have one more part. I don't want to make 4 standoffs and have 4 separate parts for each of those standoffs. I want one. All right, so one new part, and we accept. And I'll probably just stay with the standoff since that is what I called them. All right, we edit the part. I open up a sketch on the front plane. And then my standoff looks just like that. I convert the entities. And then when I go into the features, now I actually need those 2 plates. Well, I can put it in as 220, but I want to illustrate the tie-in to the references. All right, so that's actually going to be kind of small, isn't it? So the features, they get extruded, and we're not doing a from. We're going to go both directions, so up to surface, and then direction 2 gets an up to surface. And then if I decide to change the thickness of the pulley, now I have that part driven by the gap, driven by what I've determined as my offsets. All right, so having done that, I'm going to hide one of them again and accept. And when I open this, I'm going to make my life a little bit easier. Let's see, where's the origin and which way is it pointing? Kind of that way. So if I pick this edge, go into the reference geometry, set a mate reference. All right, so all of that means that I'm going to be able to drag and drop this component and not have to apply a bunch of mates. All right, so at this point, except for the bearing, we really haven't applied any mate references. Everything's tied to everything else, so we've made a big spider web of interconnected parts at this point. So I accept my my mate reference, I save this, I close it, and now the advantage, I can hide the layout, and I'm going to control select my part, drag to the next one, control select my part, so that mate reference gives me that ability to very quickly, and then I have to decide if I care if they rotate. I really don't. All right, so those were all of the standoffs. Let's go ahead and show everything. So this is also where, when in the Solidworks side, is when you get to configurations and display states. This is where I can do mid-assembly, complete assembly, or otherwise. All right, so said that I need to make a decision on the threaded connector. We'll probably end up going with a smaller one. These will have to shrink a little bit, but I want to close out the part. And now we're to the point where we can make some drawing and start to develop our process.